Hi guys, welcome back. In this video, we are going to discuss about change of variables, change of variables of an integration, right? What is the need of change of variables? First, we have to understand that just consider a function whose limits are very complex in a particular coordinate system. It's very complicated to evaluate by using those limits. So we will try to transform these particular in a, from present coordinate system to another coordinate system, where we are going to get the limits of the integral as uh, very easily, so that we can integrate the function smoothly or with less effort. Just consider if that is the scenario. If you are going to in the if you are going to transform the current coordinate system to another coordinate system, just consider the current coordinate system as f of x comma y is the current coordinate system, and we are transforming x into some another coordinate system which has its coordinate as u comma v. If we did so, the integral of the f of x comma y function will be transformed into this particular value, just like integral of f of x of u comma v comma y of u comma v into Jacobian matrix into du into dv, where j is dou of x comma y by dou of u comma v. Just don't by heart this x comma y and u comma v value. Just keep in mind that differentiation, partial differentiation of original coordinates by dou of changed coordinates. This is the thing here. Just keep in mind, and the Jacobian matrix will look like this: dou x by dou u into dou y by dou u, dou x by dou v into dou y by dou v. We have to by heart this Jacobian matrix, otherwise we will get lost in this problem. Uh, and same thing can be happened in the region where we have three coordinates. Evaluation of triple integral is far harder than double integral. So if the limits are going to be somewhat difficult, then we are going to transform those limits into another 3D coordinate system where we can easily get the limits, and it will make our integration process much more easier. The, if we did so, if we transform this coordinate system into another coordinate system, then integral of this function will become like this. Here it's j, and again j is an Jacobian matrix, as I mentioned, with respect to dou of with respect to original by change. Yeah, this is the Jacobian matrix for 3D coordinate system. Just by heart this coordinate system. Yeah, it's nothing like by hearting. Uh, it's going to be very with respect to first. We are going to perform the differentiation with respect to uh, first coordinate. Then we are going to perform the differentiation, partial differentiation with respect to second coordinate. Then we are going to perform uh, differentiation with respect to third coordinate. That's it. And as we are performing partial differentiation, we will first differentiate x and then y and then z. That's it. We cannot differentiate, we cannot take the absolute differentiation, right? So we are taking first with respect to x and with respect to y and with respect to z. If you are going to consider like dou z, dou x, dou y also, no problem. It's not a big issue. As as far as we are in the what we call clockwise direction of rotation, x, y, z. This is a clockwise rotation, right? If you're going to consider z, x, y, it's also no problem. Y, z, x, it's also no problem. As far as you are in clockwise rotation of this coordinate system, it's going to be the same thing. If you are going to change the what we call order of rotation, then we have to change this uh, de- uh, derivative terms also, that we have to keep in mind. Just take care of all these things. Now we will discuss some problem regarding this topic. States that the problem states that integrate x plus y whole square in a region. We are having a whole problem in x comma x and y coordinates, and now we will try to transform it into another coordinate system, and we will try to look at the problem how we are going to solve. In this coordinate system, R is a parallelogram with vertices 1 comma 0, 3 comma 1, 2 comma 2, and 0 comma 1. Using transformation, they have given the transformation also. Just look at this. We are going to transform into another coordinate system where the transformation of that coordinate system are also given. Just look at these things. Uh, these are original coordinate system y, x, and I'm trying to plot the values just like 1 comma 0. But in the sense, it's going to be on x-axis, right? 1 comma 0, 3 comma 1. It's going to somewhere here. I'm taking 1, 2, 3, 1, 2, 3, and it's going to be 4. Now I will plot 3 comma 1. 3 comma 1 is somewhere here, and 2 comma 2. It's going to be somewhere here, and 0 comma 1. 0 comma 1. It's somewhere like here. It's a parallelogram, right? Both sides are parallel and of equal length. Now I'm going to transform it into another coordinate system. U is x comma y, and this coordinate system, I'm going to keep the x value as 1 and y value as 0, and 1 comma 1, 1 comma 1 will be transformed as u is equal to 1 and v is equal to 1, and 3 comma 1 will be transformed as, if I keep the respective values, u will be 4 and v will be like 3 minus 2, 1, v is equal to 1. If I'm going to keep 2 comma 2, u is 4 and v is like minus 2. And if I'm going to keep 0 comma 1, I'm going to get u as 1 and v as minus 2. If I'm going to plot these values in new coordinate system, I'm going to get something like this. V, u, yeah, right? I will take it. It's minus 2, just consider, and it's 1, and it's 0, and it's 4. I'm going to get an what we call rectangle. Simple integration, right? So I'm going to integrate from minus 2 to 1 and 0 to 4. And I got the limits minus 2 to 1 and integral 0 to 4. Some function might be uh, we got u is equal to x plus y, right? And here we have function x plus y whole square dx dy. It it will be transformed like it's r, not the limits. Now I'm going to substitute the limit minus 2 to 1 integral 0 to 4 u square into j dx dy. Here j is, here this is a matrix, right? Dou x by dou u, dou y by dou u, dou x by dou v, dou y by dou v. Now I'm going to calculate. Now I'm going to calculate these values. After differentiating it, 1 plus 0 dou x by dou u and dou y by dou u, I'm going to get minus 2, like I think, yes, yeah, minus 2. And dou x by dou v is 1, and dou y by dou v is something like, sorry, it's 1, it's minus 2. Now I'm going to evaluate the this matrix 1 1 1 minus 2, and the value of matrix will be minus 2 minus 1, that equal to minus 3. But we are going to take what we call modulus of it. Now the whole integral will become integral 0 to minus 2 to 1 integral 0 to 4 u square du dv, and I'm going to integrate with respect to what we call u first and v next, because these are the limits of u, right? Integral of minus 2 to 1 u cube by 3 between the limits 0 to 4, 64 by 3 into dv. integral of minus 2 to 1. I'm going to get, I have 3 over here. It's going to get cancelled. 64 into v between the limits 1 to minus 2. 64 into 1 plus 2. 64 into 3. This is the value of the given integral. We have transformed that what we call one of the complex, this type of parallelogram. We have to like take from here to here something like horizontal coordinates. To get away from all those complexities, we just simply transform the coordinate system and we found the limits and we directly integrated it. That's it. Thank you guys. Meet you in the next video.